Cartesian products are useful when we're trying to describe the set of all possible pairings between elements of two different sets. But oftentimes we're not interested in all possible pairings. Usually we only want to pair things if they follow or obey certain guidelines. So a set R on two sets called A and B, a set R on two sets A and B called a relation, is a subset of the Cartesian product. Now remember, A cross B will give us is a set containing all the ordered pairs where the first element comes from set A and the second element comes from set B. Now the specific pairs in R are governed by a rule that we choose to obey or that we're told to obey. And the sets A and B could be the same set. Okay? So A might equal B. In other words, we want to relate elements of the same set, but this definition is just general to where that relation could be between two different sets or on one set alone. So let's consider the set A, which has the elements 1, 2, 3, 4, 5. So the first 5 whole counting numbers. Define a relation as follows. It's going to be the set of all ordered pairs A1, A2 such that the first element is less than or equal to the second element, and both of these elements that are going to be paired together are going to be drawn from the set A. Okay, so what are we looking for here? Well, we're looking for a collection of ordered pairs where the first one comes from from A and the second one comes from A, but where the element is less than or equal to the second element. Well, if I look at the element 1, well, 1 is certainly less than or equal to 1, right? Because 1 is equal to 1, and it's an OR, so one or the other has to be true. So 1 will get paired with 1. 1 is less than 2, so that counts. 1 is less than 3. 1 is less than 4, and 1 is less than 5. Now, if I keep going and now look at the element 2, well, what elements is 2 less than or equal to? Well, 2 is less than or equal to itself. It's less than or equal to 3. 2 is less than or equal to 4. 2 is less than or equal to 5. And now I can move on to the element 3. Well, 3 is less than or equal to itself. 3 is less than or equal to 4. 3 is less than or equal to 5. And now I can look at the element 4. 4 is less than or equal to 4. 4 is less than or equal to 5. And then 5 can only be paired with itself because it is the biggest element and it is in fact equal to itself, so it belongs in that set. Now, as opposed to the cross product, if I were to start listing out the elements of A cross A, well, that would be pairing every element of A with every element of A. So 1, 1, 1, 2, all the way up to 1, 5. And then I would also pair 2 with 1, right? Because in the cross product, every element gets paired with every element. So notice that 2, 1 is not in the relation because it doesn't satisfy the rule. So this will contain every single possible pairing, which will be certainly greater than the number of ordered pairs in our relation. And finally, we'd have 5 paired with every element. And how many elements would there be in this set? Well, the size of A cross A, each of the 5 elements will get paired with each of the other 5 elements. And so there'll be 25 elements in this set, 5 rows of 5 pairs. Whereas here you could see that in the first row we have 5 pairs, but then only 4, then only 3, then only 2, then only 1, because the rule doesn't allow us to pair every element with every other element. So notice that R is indeed a subset of A cross A. Why? Well, because every single element in R, every pair that's inside of R is also inside of A cross A. There's 1, 2, 1, 2, all the way up to 1, 5, and these elements are just in the dot, dot, dot right there. Let's take a look at another example. Now, it doesn't have to be less than or equal to. We could relate elements based on some other rule. So let's say the set X contains elements 12 and 24. Y contains the elements 2, 4, 6, 8. And we'll define the relation as consisting of all pairs in the cross product, but where X is divisible by Y, where little x comes from capital X and little y comes from capital Y. By the way, we don't have to use little x and little y. We could use little a and little b and still be referencing sets called capital X and capital Y. So the importance here is just to note the order and which set each element comes from. So what does it mean to be divisible by? Well, it means that if you divide that integer by that other integer, that you get a whole number. So if I start to analyze what elements are going to be in here, the first one has to come from this set. And I'm going to start off by saying, what elements from y is 12 divisible by, right? Because if I take 12 divided by 2, I get 6. So that means the pairing of 12, 2 will be a valid pairing because 12 divided by 2 is 6. So I'm only going to pair elements where the first number divided by the second number is an integer. Is 12 divisible by 4? It is. 12 divided by 4 is 3. 12 is divisible by 6. 12 divided by 6 is 2. 12 is not divisible by 8. So although x cross y would have 12, 8 in it, our relation won't, because that pair violates the rule. So now I have to move on to 24. 24 is divisible by 2. 24 is divisible by 4. 24 is divisible by 6. And 24 is divisible by 8. So notice that this is almost the size of set x crossed with set y. The size of that will be 2 times 4, which is 8. But I almost have all the elements in my relation. I'm missing, I only have 7. The size of R is 7. And the element I'm missing, of course, is 12, 8, just because 12 is not divisible by 8. It violates the rule. So once again, every element in R is an element of the Cartesian product, or the cross product, between x and y. Let's look at one more example where we're not dealing with numerical values. Let's define A to be the set of these 3 cities, Seattle, Portland, and Phoenix, and B to be the set of the 4 states, Oregon, Arizona, Washington, and Alabama. Now this is not a super interesting set, but define the relation to be the pairing of city-state. How do I know it's city-state? Not because it's lowercase, but because the first element comes from A, the second element comes from B. And only include the pairing of city-state where the city is not in that state. So it might be natural to say Seattle, Washington, Portland, Oregon, Phoenix, Arizona, but we want R to, for whatever reason, to contain the pairing of a city with a state that it is not in. So Seattle is not in Oregon, so that will be a member of this relation. Seattle is not in Arizona. Seattle is in Washington, so I don't want to include it, and Seattle is not in Alabama. Now, I do the same thing for Portland. Portland is in Oregon, so I'm not going to include Portland, Oregon, but I will include Portland, Arizona. I will include Portland, Washington, and I will include Portland, Alabama. And now I'll do the same thing for Phoenix. Phoenix is not in Oregon, so will be paired based on the rule that we've specified. Phoenix is in Arizona, so it will not be listed with Arizona, but it will be listed with Washington. And Phoenix, I could have abbreviated these, I don't know why I didn't, but Phoenix is not in Alabama. And so there is our relation. Now, once again, if I crossed A with B, I would end up with also having Seattle, Washington, Portland, Oregon, and Phoenix, Arizona. But since we've specified the rule to only include pairing of city to state where the city is not in the state, this is still a valid cross product between A and B, but it doesn't include the ordered pairs that we think would naturally belong because of the way we've defined this relation. Why we would want to do this, I'm not entirely sure, but I think it challenges our thinking to really focus on the definition rather than just what we know to be true.